Hello everyone. In this section, we will talk about confidence intervals for the difference of two means. And there are many applications for finding the confidence interval of two different means. Comparing new design to old design, I'm finding the mean amplification of design number 1 and I want to compare it to the mean amplification of design number 2 and finding the difference to see if there is big difference between them. Before we start, just a review. If I have a random variable with a normal distribution with mu x and sigma x and another random variable with normal distribution with mu y, sigma y. Now if I add these two random variable x and y, then the mean will be the sum. So let's call this z equal x plus y. Then the mean of z will be the mean of x plus the mean of y. The variance of the sum x plus y will be the variance of x plus the variance of y. If I find the difference x minus y, then the mean of x minus y will be the difference between mu x minus mu y, and the variance will be the sum. As we did before, it doesn't matter you add them or you subtract them, the variance will be always the sum. And we have covered these in previous sections. So let's apply some of these facts to the following. Now assume you have two populations and you took a large sample from each population here, and I don't know what's the mean of this population. Let's call this is x and this is y, and I don't know what is the mean of this population. I want to find the confidence interval between mu x minus mu y. So as we did before, we take a sample from this population and usually larger or equal to 30 samples here, same thing here, equal or larger than 30. They don't need to be the same, but they have to be larger than 30. Then we find the sample mean here x bar and the sample mean here y bar. If I know sigma x, then I will use it in the confidence interval. Same thing here, if I know sigma y, then I will use it. If I don't know them, then I will use the sample standard deviation Sx and Sy. Now the confidence interval between the means of the population X and the mean of the population Y will be the difference between X bar minus Y bar plus minus Z alpha over 2, and Z alpha over 2 will depend on the confidence level we use to find the confidence interval. And the standard deviation of the difference. Square root the variance of x squared divided by nx, which is this one, the size of the sample from population X, plus the variance of y divided by ny. So you could have created a random variable, call this z, then this will be the mean of z, and this will be the standard deviation of z. Then the steps will be the same as we did in earlier sections. Okay, let's take this example. The chemical composition of soil varies with depth. An article in Communications in Soil Science and Plant Analysis describes chemical analysis of soil taken from a farm in Western Austria. 50 specimens were each taken at depth 50. So we have a soil depth 50, and this is a soil of depth 250. And we took a sample n equal 50. So let's call this x. And we took a sample here, let's call this y, and ny equal also 50. Okay, at depth 50 centimeter, the average nitrate concentration in milligram per liter was 88.5. X bar here is 88.5 with a standard deviation of 49.4. Sx 49.4. At depth 250, the average concentration was 110.6. So y bar is 110.6 with a standard deviation 51.5. SY 51.5. Find a 95 confidence interval for the difference in nitrate concentration at the two depths. So our confidence level is 95. So alpha equal 1 minus confidence level. So that is 1 minus 0.95 equal 0.05. So then the confidence interval will be x prime minus y prime plus minus z alpha over 2, the standard deviation of the difference, which will be sx squared divided by n plus sy squared divided by n. So that is 88.5 minus 110.6 plus minus z alpha over 2, where alpha over 2 in this case will be 0.025. And if we use the table for a standard normal distribution to find what is z here, such that this area here 0.025, it will be 0.025 here. So that is z minus 1.96, because again this plus minus, so that's 1.96 times sx is 49.4 square divided by 50 plus 51.5 square divided by 50. And if you calculate these, you will get minus 22.1 plus minus 19.78. That's the difference between nitrate in a soil 50 centimeter in depth versus a soil 250 centimeter in depth. So there are more nitrate in the deeper ground. And this problem actually is similar to a senior design project where a student try to estimate the resistance of the soil when it is dry and when it is wet. Supposedly when it's dry, the resistance of the soil will be larger, so then that will help them make a decision, or their auto irrigation make a decision when to turn on the water sprinkles, depend on the dryness on the soil. And they use this technique to see if there is a big difference in resistance value of the soil when it is wet versus when it is dry. Okay, so let's look at another example here, example 10. The article, The Prevalence of Daytime Napping and Its Relationship to Nighttime Sleep, published by McWhiskey and Kerrigan, Behavioral Medicine magazine, presents result of study of sleep habits in a large number of subjects. In a sample of 87 young adults, the average time per day, so we have here a sample of young adult, n equal 87, young adult, let's call it x. The average time per day spent in bed, either awake or asleep, was 7.7. X is 7.7, with a standard deviation of 1.08 hour. And the average time spent in bed sleep was 7.06 hour. Now here they could be sleep or not, but the average time, let's call this y, they are asleep, and they found it to be 7.06 hour with a standard deviation SY equal 1.11 hour. The mean time spent in bed awake was estimated by x minus y, which is 7.7 minus this, and it came 0.64 hours. Is it possible to compute a 95% confidence interval for the mean time spent in bed awake? If so, construct the confidence interval. If not possible, explain why not. Well, here we cannot say the actual sleeping time 7.06 is independent from the actual time 7.7 laying on bed and flipping around until they fall asleep. And because there is dependency between both cases, we cannot assume x and y are independent random variable, and the variance of x prime minus y prime will be the same as the variance of x plus the variance of y. That is true only if x and y are independent. So this x and y, we cannot assume they are independent, so we cannot use this one, and we cannot find the confidence interval with a specified confidence level using the method we learned. All right, next section we will talk about confidence interval for the difference between two proportions, and we use these to compare performance of two assembly line or performance of two different algorithm or medical procedure. So we may have procedure X or algorithm X and Y, and we are interested in comparing the proportion of X and the proportion of Y. For example, we may transmit bits or packets, and I want to compare this method X, the proportion of success arrival, versus this method Y. So how do I compare the difference so I decide which algorithm or which procedure I go with or which assembly line is better? Then I will try to find a confidence interval with a specific confidence level of the difference between Px and Py. And I don't know the value of Px and Py. So we take a sample, large sample nx 30 or more, and a sample from here, and that is not ny. Then I count x is the number of success in the sample and y is the number of success in this sample. So we estimate as before the probability x, which is the probability of success. It's the number of success divided by all items or trial in the sample, which is nx. Same thing here will be y, the number of success in the sample, divided by ny. Now, if I want to compare the difference, then I need to find a confidence interval for px minus py. As before, the difference plus minus the standard deviation of px minus py times the alpha over 2, which will be determined by the confidence level. Now, if I try to find the standard deviation of this quantity, let's find the variance of px hat minus py. That will be the variance of px hat plus the variance of py hat. As we said before, when you have x plus y or x minus y, the variance always going to be the variance of x plus the variance of y. This is a Bernoulli trial. So the same thing we learned in chapter 2, px times 1 minus px divided by nx. And this one, it will be py times 1 minus py divided by ny. And if I take the standard deviation, it's just the square root of this. So this confidence interval then will be px hat minus py plus minus z alpha over 2 square root of this quantity. And that's the confidence interval of the difference between the proportion in this population and the proportion in this population. If I don't know what is these values, so I estimate them by taking a sample here and the sample here of a large size, and that will be the confidence interval of the difference. As before, if the sample nx is very large, like above 1,000, then this is correct. If nx is like 30, 50, 70, then this will tend to be very narrow confidence interval, so we do the correction. Instead of using px x over nx, now we're going to have px tilde, which will be add to number of success 1 and to the size of the sample 2. because we have now px and py. So we just add in the numerator 1 and the denominator 2. Before, if I am trying to find the confidence interval of just px without py, one variable, then I add 2 in the numerator and 4 in the denominator. Same thing, py will be y plus 1 over ny plus 2. And I define nx delta equal nx plus 2, and the same thing ny delta is ny plus 2. And if I use these instead of hat, I use this delta, I get a better confidence interval. That means if I run the experiment or simulation many times, actually it will meet this confidence interval more accurately than using these. So regardless, if the nx is large, they will be the same. But if nx is small, then this is more accurate based on simulation and testing. Now, when you calculate this quantity, you may get minus 1.5 and you may get 1.8. But we know the smallest possible this quantity can be is when proportion of x is 0 and the proportion of y is perfect, 1. That means all production or transmission arrive with no error. So that is 100% success. So that will be 1. And in this population, 0% success. So that will be 0. So the maximum you can get is minus 1. So if you get minus 1.5, when you finish calculating this, round it to minus 1. Same thing, the maximum value this can be is when px is 1, so the population is total success, and py is 0. That means 0 success. So 1 minus 0 is 1. So the maximum it can be 1. So if you get these, then round it to 1. So let's look at this example. Angioplasty is a medical procedure in which an obstructed blood vessel is widened. In some cases, a wire mesh tube called a stent is placed in the vessel to help it remain open. The article Long-Term Outcomes of Patients Receiving Drug-Eluting Stent, published in 2009, found the following, or presented the following. The result of a study comparing the effectiveness of a bare metal stent with one that has been coated with a drug designed to prevent reblocking of the vessel. So they did this study. A total of 5,320 patients received bare metal stent. So this is our sample X, bare metal stents. So we took a sample from here of size nx equal 5,320, and we found, and of these 841 needed treatment for reblocking within a year. So 841, so x equal 841 that need retreatment after 1 year surgery. A total of 1,120 receiving drug-coated stent. So let's define this population Y, drug-coated stent. So they took patients or a sample NY equal 1,120, and they found the number of patients that need treatment Y equal 134. Find a 98% confidence interval for the difference between the proportion for drug-coated stent and bare metal stent. So the confidence level is 98%, and they want the confidence interval of px minus py. Well, we're just gonna follow these. So we have to estimate these and estimate these, and then the standard deviation, and find z alpha over 2 for 98% confidence level. So px delta is number of patient need retreatment 841 plus 1 divided by the total number of patients 5,320 plus 2. And if you calculate these, you should get 0.1582. Let's point estimate for py delta is 134 plus 1 divided by 1,120 plus 2. And if you calculate these, you should get 0.1203. So the confidence interval then will be this minus this one. So that will be 0.1582 minus 0.1203 plus minus z alpha over 2. That is z Let's find alpha. Alpha will be 1 minus the confidence level. So 1 minus 0.98, that is 0.02. Alpha over 2 is 0.01. So we need to find 0.01. Square root px, which is 0.1582, times 1 minus px, which is 0.1582, divided by n delta, which is 5320 plus 2, plus the variance py, which will be 0.1203, 1 minus 203, divided by 1120 plus 2. And if I try to find what is this z using the standard normal distribution, so we're going to use the table to find what is this. For a probability, this area here should be 0.01. And if you do that, if you look at the table, you should find this minus 2.325. So if you calculate, then confidence interval will be, if you calculate this, you should get 0.0378 plus minus. If I plug for this quantity and then multiply it by this, I should get 0.0254. So if I convert these to a percentage, it's like 3.78% plus minus 2.54%. So the proportion of patients that need treatment within a year after the surgery, the difference between the metal and the coated one, it could be as much as you add these two. So it could be as large as 6.3%, and the difference can be as low as 1.25%. So with the stent, with the coated drug, it improved the difference in comparison to the non-coated drug, 6.3%. Less patients that need treatment after 1 year. Thank you for watching, and the next video in chapter 5 will be about confidence intervals with paired data and confidence interval for the variance and the standard deviation of a normal population. Thank you.